Okay, we are almost done with our moving charges with magnetism unit. We have today and one more lesson after that. And what we'd like to do, just as a reminder, is create electricity using magnetism. The answer to this problem is going to change humanity forever. We're going to be able to create electricity using magnetic fields. We already saw a way of doing this that's extremely impractical, and that was just pushing a metal bar through a magnetic field along a series of rails. We got a formula for the induced voltage, and we saw that we could use that induced voltage just like we'd use any other voltage using Ohm's law. We saw that the electricity flowed through our circuit, and we explained why, and we saw we could use it to light up a light. This is going to be of limited use because after pushing this bar a little bit, we're eventually going to run out of rail. And this is not going to be sustainable over the long term. We want a better option. That better option will involve a coil of wires and a magnetic field. And we did a little experiment where we did all kinds of changes. We changed the horizontal position, the vertical position, we rotated it, we flipped the magnet, and we did a few other things. We saw that some things made the light bulb light up, meaning we had electricity. And some things, the light did not light up, meaning they were ineffective at causing electricity to flow through our coil. And it seemed to be pretty random about what things would make it light up and what things would not. So what we'd like to do over the next couple days is try to figure out what common theme was present every time the coil created electricity. That is going to be key to understanding induced currents. In order to do that, though, we need to take a step back and look again at our solar panel and what we learned in this lab on the solar panel. So start with a drawing. You got your solar panel, you got sunlight, and down the bottom, just to make sure it's clear, this is a shadow cast by the solar panel. That is going to be an important thing. All right, so from the solar panel lab, we want to make sure you understand the idea of flux. And this is a term that you are not familiar with. So you're probably thinking, what is flux? Let's go a little deeper to figure out what flux represents. First of all, I want to make sure you know in this example, this number is going to be a direct indication of the flux for the solar panel. All right, so you can see that this solar panel is collecting about 1.9 kilowatts, which again would be about 1,900 joules per second. All right, so that's going to be a measure of the flux. The bigger that number gets, the more flux we have with the solar panel. All right, so what factors influence how much energy we collect? That is, what factors influence flux? The first factor is pretty obvious, the area of the solar panel. More area means we're going to collect more energy. You see, we went from about 1.9 up to about 4.7. It went up tremendously. It turns out to be a proportional relationship. If you double the area, you will double the flux. Doubling the area doubles the flux. Factor number one. This is why we want to have big solar panels. The bigger the solar panels, the more flux we are going to be able to have, which means we're going to be collecting more energy. Okay, factor number two is our solar constant. The unit, I kind of messed that up. The solar constant should be watts per meter squared. That is how many joules per second are hitting the solar panel per meter squared. Okay, it is a measure of the strength of the sunlight. So that solar constant is a strength of the sunlight, 1,100 watts per meter squared. If we went to the upper atmosphere, right where the atmosphere kind of starts, the solar constant at that spot for Earth is about 1,300 watts per meter squared. At the surface of the Earth, it's closer to 1,100 watts per meter squared. So if you're doing a problem with a satellite going around the Earth, use 1,300. If you're doing a problem with a solar panel that's actually on the surface of the Earth, you'd want to use 1,100 watts per meter squared. We're losing 200 watts based on the scattering of the light, the absorption of the light by the atmosphere. Now realize from day to day, this number will not change. This number might, based on cloud cover and whatever else might be happening in the atmosphere, forest fires or whatever. All right? So that's our solar constant, the strength of the sunlight at the position of the solar panel. It's measured in watts per meter squared. Okay, again, if we watch our flux, we will see that when we make a change to the solar constant, we change the amount of flux. A bigger solar constant will give us a bigger flux. So we have two factors so far. The area, which has to be measured in meters squared, obviously, and the solar constant, which is measured in watts per meter squared. When we multiply those two together, I hope you see the meter squared cancels out and it tells us how many watts we are collecting at the solar panel. All right, so they are the two factors so far affecting flux. It turns out that there is one more factor that's really important, and that is the angle of our solar panel. So take a look. At an angle of 0, look at the flux. And then look as we raise the angle and we go closer and closer to 90 degrees, you'll notice that the flux gets lower and lower and lower. So the third factor that affects the amount of flux is the angle of the solar panel. I can see this with my own house. This is the roof from my back porch. You'll see the left side and you'll see the right side. Both of these have the exact same area. Both of them are getting the exact same solar constant. It's the same sunlight hitting both sides of the roof. So why did one melt and one didn't? It's because this side has a higher flux based on the angle. This one is angled away from the sun, so it's got a lower flux. So even though we have the same solar constant and the same area, we also have to worry about angle. We want to angle it toward the sun to collect the most energy. Okay, it's a little tricky how we are going to do this. So I want to make sure you understand how we are going to turn area into a vector. I hope you remember the term vector. It's a quantity that has a direction. And when we went through our vectors, you probably never thought of using area as a vector. How could area have a direction? Well, it turns out there are many cases in physics and mathematics where we really need to assign a direction to area, and this solar panel is a great example. Now, you'd be tempted to put the area vector, the direction, some direction on the solar panel itself. So maybe you'd have it pointed to the right. Maybe you'd have it pointed in this direction, maybe this direction, maybe this one. And we ask, which of those is correct? And the answer is none of them. They are all equally invalid. They don't help us. To make this unambiguous, the rule for area vectors is always point the area vector perpendicular to the actual area. So even though the area, the solar panel, is horizontal, we're going to point our area vector 90 degrees to that. So the area vector would point in the y direction, even though the solar panel is in the x and z directions. All right, so there it's unambiguous. The panel is horizontal, the area vector points vertical. Again, the problem is if we tried to draw our area vector horizontal, there's an infinite number of different directions we could point it. If we point it perpendicular, we have restriction that would have to be in the y direction. All right, so hopefully you understand what I was saying. Area vector points perpendicular. So here's just two more pictures just to make sure you're clear. To find the area vector, you do length times width, you'd figure out your area, and then you'd point it perpendicular to the actual surface. So if the surface is horizontal, you point your area vector vertically. Here we have an area that is on an angle. You'd calculate your area, you'd do pi r squared, and then the direction would be a 90-degree angle to however this circle is tilted. All right, so your area vector points perpendicular. All right, so just so we're clear, here are the two extreme examples. Here is an area vector that has a 0-degree angle to the sunlight. I hope you guys see both the sunlight and the area vector are pointing in the same way. They are both along the y-axis, so there is 0-degree angle between the two. Okay, here we have a 90-degree angle because the area vector is pointed horizontally and the sunlight is vertical, 90 degrees. You'll see 0 degrees is our best case. It's the one where we had the highest possible flux. 90 degrees is the worst case. That's going to give us a flux of 0. None of the sunlight is actually hitting the solar panel. And this is where I hope you understand that the shadow is key to how much sunlight has been absorbed by the solar panel. When you have a big shadow, that means a lot of the sunlight has been taken away by the solar panel. When you see no shadow, none of the sunlight was absorbed by the solar panel. So the shadow is a great tool to give us a feel for how much energy we've taken away. Okay, so finally, just to make sure you're clear, if we have an angle of 45 degrees, that means our area vector is pointing like this. Our sunlight is like this. And this is what we're talking about for the angle, theta. In this case, 45 degrees. If we wanted to figure out the actual flux using a mathematical formula, what we would do is we say flux equals the solar constant times the area, and then we do times, cosine of the angle between them. Remember that the cosine of 0 is 1, and the cosine of 90 is 0. So at a 0-degree angle, that would give us our best case, and 90-degree angle gives us our worst case. Okay, so I just want to make sure you're clear. This whole idea of angle is what gives us our seasons. So depending on the time of the year, based on the tilt of the Earth, determines what angle the sunlight is actually hitting the surface of the Earth. It's kind of like that back porch. When we're angled toward the sun, that would be like this. This would be like summer. And we're angled more away from the sun. This would be more like winter. So the angle between the sunlight and our surface is going to help determine how much energy we are actually collecting, whether it's on the surface of the earth or on a solar panel. All right, so I'm going to stop right here and just make sure you understand that what we're doing going forward. We only have one more lesson, and we're hopefully going to put everything together to see how this idea of flux for the solar panel will help us determine, is the light bulb going to be lit? Are we going to be generating electricity or not? A very key question for determining how we are going to get a valid, viable source of electricity using a magnetic field. So hopefully this all made some sense.